As I mentioned, there's multiple components of this course, and before we get into programming, which I'm sure that's what everybody's here for, we have to go through the numbering systems and the underlying logic and microarchitecture that supports those numbering systems. Chapter 2 gets us started on that path. We'll cover bits, data types, and operations. So, how do we represent data in a computer? And at the end of the day, a computer, a microprocessor, at the smallest level of detail, only understands that a circuit is charged or it's not. So this works by controlling the flow of electrons. And there are two conditions at the smallest level of detail in a computer. That is the presence of a voltage, we call state 1, or the absence of a voltage, we call state 2. Now, you've all seen this in everyday life. You walk up to a switch on the wall, and let's say it's connected to a single lamp, and you throw the switch to the on position, which in this case would be 1. Electrons flow through the wiring to the light, and the light goes on. You throw the switch to the off condition, and the light goes off. So we base a state on a value of voltage, but control and detection circuits are more complex. Computer is a binary digital system, and the basic unit of information, the smallest unit of information, is the binary digit or a bit. And that bit carries values 0 or 1. So it has two states, if you will. State 0 means there's no voltage. State 1 means there is voltage. Now, we're going to combine multiple bits to represent values with more than two states. So if one bit has two states, 2 bits has 4 possible states. A collection of 3 bits has 8 possible states. So the general rule we're getting towards here is that a collection of n bits has 2 to the n possible states. 1 bit has 2 states. 2 bits, 4 states. 3 bits, 8 states. 4 bits, 16, 32, 64, 128, 256, 512, 10. You get it. Each time we add an additional bit to a binary number, we double the number of possible states or values that it can represent. What kind of data do we need to represent? Well, you think about it. What do you use a computer, a computing device to represent? You listen to music? Sure. You view images? Yes. Full motion video? Yes. Numbers, text? Obviously. So, in this course, we're going to learn how data is represented in various numbering systems so that it can then be used by us humans. Okay? We're going to start with numbers. Now, I'm going to guess most, if not all of us here together now were raised counting with the base 10 numbering system. So when you were born, you were 0. We don't typically talk about that, but you were 0. And then 365 days later, unless it's a leap year, you have your first birthday. And then 365 days after that, second birthday, represented by 2. 3, 4, 5, 6, 7, 8, 9. So when you're 9, you've exhausted all of the digits in the base 10 system. There are 10 digits, 0 through 9, 0 through n minus 1, 10 minus 1. So when you, on your 10th birthday, you've been alive for 3,650 days, you need a second digit to represent that number. So my job in this course is to convince you that learning a base 2 or a base 4 or a base 8 system is easier. We're not going to learn a base 4 or a base 8 system, just putting it out there, is easier than the system that we use every day. So binary may look cryptic because it's a series of zeros and ones. It's actually less cryptic than the system we've been using all our lives. So let's start with unsigned integers. We have 2 numbers, okay? And they have positional notation. 329, which is represented as a base 10 number, is actually, let's dissect it. It's 9 times 10 to the 0 plus 2 times 10 to the first power, which is 20. 9 times 10 to the 0 is anything to the 0 is 1, so it's 9 plus 20 plus 3 times 10 squared to the second power, which is 100. And you add those 3 up and you get 329. So to the right of that, we have a binary number, 101. Okay? Its least significant digit or bit is 1 times 2 to the 0. Just like we had 9 times 10 to the 0, but this is a base 2 number. So we've got 1 times 2 to the 0, which is anything to the 0 is 1. So we've got 1 times 1, plus 0 times 2 to the first, plus 1 times 2 to the second. 2 to the second, 2 squared is 4. So we've got 4 plus 0 plus 1, 5. So 101 in binary is the equivalent of 5 in a base 10 or decimal. See? How many digits do we have to remember to represent values in a base 10 system? We have to remember and use 10 digits, 0 through 9. In a binary base 2 system, we have to use how many? 2, 0 and 1. I rest my case. Technically, binary is less complex than decimal. Easy to say, harder to implement. Because, why? We've been raised in a base 10 system. Here's the problem. Computers do not process data in a base 10 system. They're based upon presence of voltage, no presence of voltage, 0, 1, etc. Okay, so let's take a look at 2 numbers, one base 10 binary number,
1101, and then one base 10 number or decimal number 329. The rules of engagement are exactly the same. So on the 329, let's come down here. So we've got 9 times 10 to the 0, right? Sorry. Okay. And that is 9. Here we've got 2 times 10 to the first, which is 20. And then we've got 3 times what? 10 squared, which is 3 times 100, which is 300. So obviously those yield 329. So let's come up here, take a look at our base 2 number, right? We've got 1 times 2 to the 0. Anything to the 0 is 1, so we've got a 1. We've got 0 times 2 to the first. 0 times anything is 0. We've got 1 times 2 squared. What's 2 squared? 4. So we got 4. And then we've got 1 times what? 2 cubed. 2 times 2 times 2 is 8. It's pretty easy. 8. 8, 12, 13. This number is 13 base 10.
Here we have a chart that shows the first 3 digits in base 2. And so I just did a 4-bit number. This is a 3-bit number. 0, 0, 0, obviously 0. 0, 0, 1. And you could do it backwards. 1 times 2 to the 0 plus 0 times 2 to the first plus 0 times 2 to the second, 1. 0, 1, 0. 0 times 2 to the 0. 1 times 2 to the first, 2. 0. So just to give you some pattern recognition hints, whenever bit 0 is a 1, you have an odd number. Whenever bit 0 is a 0, you have an even number. See? 0, 2, 4, 6. Bit 0 is always 0. 1, 3, 5, 7. Bit 0 is always a 1.
Our next topic is binary addition. But before we add 2 binary numbers, let's talk about overflow. Overflow happens when a digit exceeds its capacity. And here I have 2 obviously base 10 numbers because they have digits other than 0 and 1. And let's just talk about what happens when you add 99 plus 1. Well, 99 is the largest value that can be represented with a 2-digit base 10 number. So when we add 1 to 99, we're going to exceed, or we're going to overflow, the capacity of each of those 2 digits. So how do you do this? 9 plus 1 is what? 0. And you have a carryover, right, of 1. 1 plus 9, and you could, in effect, put a 0 here, right? 9 plus 0 plus 1 is 0, and you carry over a 1. So in order to represent the sum of 99 plus 1, we must have 3-digit capacity, and that's 100. It works the same way for binary digits. Next slide, we're going to show you some examples of binary addition. But remember, it works the same way. Once we exceed the capacity of a bit, we have overflow.
Here we have several unsigned binary arithmetic problems. Base 2 addition. It's just like base 10. So let's take the first one on the left. 1, 0, 0, 1, 0 plus 1, 0, 0, 1. They don't have the same number of bits. Not a problem. The second operand, 1, 0, 0, 1, you can just place as many zeros as you want in front of that because they don't have any magnitude. So in this example, we'll start with column 0, 2 to the 0. 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 1, and we'll just place a 0 there. 1 plus 0 is 1. So the result is 1, 1, 0, 1, 1. Wow, that was hard. No big deal, right? There's no carryover. Let's go to the next example to the right. Start with the first digit, bit 0. 0 plus 1 is 1. No big deal. 1 plus 1, just like 9 plus 1. 1 plus 1 is 0, but we carry a 1. So then we have the carryover plus 0 plus 0, 1. See it? 0 plus 1, 1, 1 plus 0, 1. Now, let's take the third. This is the equivalent of 9,999 plus 1 in base 10. 1 plus 1 is 0 with a carryover. The carryover is added to the 1. So 1 plus 1, and you could say there's a imaginary 0 there, is 0 carry 1. Carry the 1. 1 plus 1 is 0 carry 1. 1 plus 1 plus 0 carry the 1. So 1, 1, 1, 1, base 10, I'm sorry, base 2, 1, 1, 1, 1, oh, I almost blew the whole thing. 1, 1, 1, 1, base 2 plus 1 base 2 is 1, 0, 0, 0. So let's translate those numbers to their base 10 equivalent. What is 1, 1, 1, 1? Well, we did that earlier. It's 1, 2, 4, and 8. 8 plus 4, 12, 13, 14, 15. That's 15. That is the largest value that can be represented with a 4-bit number. It's 2 to the 4 minus 1. 2 to the 4 being 16. So that's 15 plus 1, right? Because 1, 1, 1, 1 was the largest value we could represent with a 4-bit number if we add anything to it, anything other than 0, obviously. If we add anything to it, we're going to need at least a 5-bit system or value, or digit, 5-digit number to represent the result. So that is 15 base 10 plus 1 base 10 gets us to 16. So we've got 0 times 1, or 0 times 2 to the 0, 0 times 2 to the first, 0 times 2 to the third, 0 times 2 to the fourth. I'm sorry. 0 times 2 to the 0, 0 times 2 to the first, 0 times 2 to the second, 0 times 2 to the third, 1 times 2 to the fourth, which is 16.
Now let's finish what we started on the previous page. So 1 plus 1, 0. Carry the 1. 1 plus 1 is 0, and we got a carryover. Plus 1 is 1. We got the carryover. 1 plus 1 is 0, plus 1 with the carryover. 1, 1, 1. Right? So let's back into this. What is the sum? Well, I'm going to do it the quick way. I'm going to start at 1 and I'm going to count up. So I got nothing in 1, 2, 4, 8, 16. 16, 8, 24, 28, 29, 30. So the answer we got was 30. Now let's double check that. So I'm going to start at bit 0, 1, 2, 4, and 16. That's 16 and 7. That's 23. And what do we have here? 1, 2, 4, 7. 23 and 7. You got it.
So far, the binary numbers we've explored have all been unsigned integers. We haven't dealt with positive or negative values yet, but we will. We have to. So one way of doing it is looking at n number of bits gives us 2 to the n distinct values, such as when we had 3 bits, we could go from 0 to 7. What is 7? 2 to the third is 8, so 7 is 2 to the third minus 1. If we had 4 bits, we could go from 0 to 15. What's 15? Well, 2 to the fourth is 16 minus 1. So we could assign half the bits to positive and half the bits to the negative, but that leaves 2 values for 0. And that's not going to work real well. So I'm going to cut to the chase. We don't use a sign and magnitude system. We don't use 1's complement, which is flip every bit to represent negative, because that leaves us with 2 zeros, one on the negative side and one on the positive side, and 0 is neither. So we use a system called 2's complement. And I have to tell you, I found a video series on YouTube by a fellow named Rodney Crater, and I've been using it for years. And I don't think I could do a better job of producing a video that explains 2's complement. So what we're going to do, and I'll tell you when, after we talk about 2's complement for a little bit, I'm going to ask you to pause this and watch those 2 videos, which I've placed in the timeline for Canvas. Rodney is a really good communicator, and I think he does a great job of explaining the 2's complement numbering system. And just so you know, this is not an academic endeavor. We are going to program in machine language using the x86 instruction set architecture, and the x86 instruction set architecture uses 2's complement addition to calculate offsets, operands, all kinds of things. So this is not something we're going to have to get through just for test number 1. We are actually going to use this for the rest of the class. Well, there'll be a slight pause when we get through the other numbering systems, but as soon as we get into programming, 2's complement will be front and center. So this is not something you want to skimp your studying time on. Okay, before you go any further, I need you to watch these 2 videos, part 1 and part 2 on 2's complement. If you don't, you're going to be lost. It really is that important. Not only will you be lost for the rest of this lecture, and not only that, but you will probably bomb exam number 1. It is that important. And then when we get to the programming part, if you don't understand 2's complement, it's going to be a bad scene for you. Now, if you have any questions about 2's complement, or you need me to log in live with you, either during my office hours or some other time via GoToMeeting, I'll gladly do that. But please don't proceed past this point without a thorough understanding of 2's complement. So go watch those videos. Did I mention that? Go watch those videos. As was noted in the videos you just watched. You did watch them, right? I know if you didn't. I will know if you didn't. Anyway, problems with sign of magnitude in 1's complement. You got the 2 representations of 0, positive 0 and negative 0. It's almost impossible to handle that in a digital circuit. So 2's complement representation was developed to make circuits easier for arithmetic. So somewhere way back when, the designers of the circuitry sat down with the engineers and said, how are we going to represent signed integers in binary digits? And they walked through the various scenarios. Now, obviously, I wasn't there, but I'm pretty sure this is an accurate depiction of what happened. And everyone agreed on 2's complement as the easiest way to implement signed arithmetic using binary numbers. So if you have a negative number represented as a 2's complement binary value, you're going to have a 1 in the most significant bit. So here, if you want to represent 5 as negative 5, you simply follow the process. You flip the bits to get the 1's complement, and then you add 1. And that's shown in the addition on the left of this slide. 5 is 00101. You flip the bits, and you add 1, and there is your negative 5. In the addition problem on the right, you've got 9. And in this case, we're using, for whatever reason, a 5-bit representation. And we flip the bits, and we add 1. I'd like you to do that on your own. I can tell you what the answer is going to be, but I'd like you to do that on your own. Here, I'll give you 7 seconds. No, I'm just kidding. I'm not going to. I could easily complete that problem there, but I'd like you to do that on your own and then check your math.
Okay, so let's take a 2's complement number. Obviously, this number is, if represented in 2's complement, it's positive because our most significant bit is 0. Okay, so how do we, and this 1, 2, 4, 8, so 8 and 1, it's 9. So this is 9 base 10. How do we convert that to negative 9 using 2's complement? Well, here's the process. We flip the bits, 1, 0, 1, 1, 0, and then we add 1. Okay, we've got 1, well, I should do it backwards, 1, 1, 1, 0, 1. That, my friends, is negative 9 base 10. We're going to do quite a bit with 2's complement because 2's complement is used extensively in the instruction set architecture that we will be learning in part 2 of this class. Part 3, part 2, I don't know. The majority of the second half of this class, probably 60% will be spent programming in machine language and assembly language. And they use 2's complement for everything. Operands, offsets, shifts, subroutine calls. It's all over the place. So this is not a one and done. I need to memorize a series of rules for exam number 1 and then I'll never see this again. No, you will see this extensively.
Here is a shortcut for 2's complement. On the left-hand side, you'll see the traditional flip the bits and then add 1. On the right-hand side, you'll see the shortcut, which, to be candid, I don't use the shortcut. I don't know why, I just don't. But either one works. You just have to be careful. So you copy the bits from the right to the left until and including the first 1. And then you flip the remaining bits. And if you look at the 2 numbers, they're the same. These 2 work out to be the same. I find it awkward because a lot of times if you have a 1 in bit 0, it doesn't really buy you much. You don't really gain much of an advantage. But anyway, whatever works for you, both methods are appropriate for this class. Take a good look at the normal way and the shortcut. Here's a chart showing how the capacity of binary numbers are split in order to accomplish one side positive, one side negative. So in essence, what you see is 0 gets pushed onto the positive side. And so with a 4-bit number, which typically would allow you to represent 16 values, 0 to 15, we can represent 8 positive and 8 negative values if you think of 0 as being a positive value. That's a little bit of a leap, but there it is. So you can go 0 to 7, -1 to -8 with a 4-bit 2's complement signed integer value. It's really simple to convert a binary 2's complement value to its decimal or a base 10 equivalent. We've already converted unsigned binary numbers to base 10 decimal numbers. So if the leading bit is 1, that indicates it's a negative number. So you just take the 2's complement to get the positive number, and then you know what to do, right? Add the powers of 2 that have a 1 in the corresponding bit position. If the original number was a negative, you add the negative sign in front of it. It's really straightforward, easy to do. Here we have 2 more examples. The first, 001, 00111, base 2, is obviously a positive number because the most significant bit is a 0. So that's just simply adding 1 plus 2 plus 4 plus 32. I just went left to right, right to left. 1, 2, 4, nothing in the 8, nothing in the 16, 32. It's easier to write these down. So that number is 39 base 10. The second example, 111-00110 base 2, is obviously, well, maybe not obviously, but I should say it's a negative number. Why? Because the most significant bit is a 1. So we're going to flip all those bits, right? And we'll add 1. And so then we've got nothing times 0 times 2 to the 0, 1 times 2 to the first, 0 times 2 to the second, 1 times 2 to the third, 1 times 2 to the fourth, and all zeros. So we've got
16 plus 8 plus 2, 26 base 10, and we add the negative number, no, I'm sorry, the negative sign in front of it because we started with a negative number. Next up, how to convert a decimal number to a binary 2's complement number. There are two methods. First method involves division. Find the magnitude of the decimal number, always positive, divide by 2, and the remainder is the least significant bit. Now, step back for a second and listen to what I'm about to say. Remember when we were looking at binary numbers? Bit 0 is always 1 or 0. And if the number is even, it's going to be a 0. So if you divide the number by 2, if it's an even number, bit 0 is going to be 0. If you divide it by 2 and it's odd, bit 0 is going to be 1. So that's a big hint as you get started. So you keep dividing by 2 until the answer is 0, writing the remainders from the right to the left. So in this example, we take 104 base 10. Now you have to think about that for a second. That 104 is going to have bit 0, 0, right? Because it's an even number. So 104 divided by 2, 52 remainder 0. Bit 0, 0. So you write down the 0. 52 divided by 2, 26 remainder 0. So bit 1 is 0. 26 divided by 2, 13 remainder 0. Bit 2 is 0. 13 divided by 2, 6 remainder 1. Bit 3 is going to be 1. 6 divided by 2, 3 remainder 0. Bit 4 is going to be 0. 3 divided by 2, 1 remainder 1. Bit 5 is going to be 1. 1 divided by 2, 1 remainder, I'm sorry, 0 remainder 1. There's bit 6. So then you assemble the number right to left, 0, 0, 0, 1, 0, 1, 1, 0. That was right to left. That is the equivalent of 104 in base 2. Now, obviously, if it was a negative number, right, you take the 2's complement, and you'd see the leading 0 would become a 1. The next method of converting a decimal to a binary 2's complement number involves subtracting powers of 2. So we start again with 104. Find the magnitude of the decimal number 104. If it were negative, we'd still use 104, and then we'll flip the bits at the end and add or take the 2's complement. So in this example, you have to find the largest power of 2 less than or equal to the number. So 1, 2, 4, 8, 16, 32, 64, 128. So it's not 128, it's 64. And 64 corresponds to bit 6. See the little chart on the right-hand side of this slide? Okay, so bit 6 is 1. 104 minus 64 is 40. Okay, well, 40 falls between 32 and 64, so we subtract 32, and bit 5 becomes 1. And then we have an 8. 8 is exactly divisible by 2, so 8 gives us bit 3. 8 minus 8 is 0. We're done. So we assemble the number with bit 6, which is the most significant bit in this case. 6 is a 1, 5 is a 1, 4 is a 0, 3 is a 1, 0, 0, 0, base 2. Now that we have a good handle on signed integers and unsigned integers, let's take a look at some arithmetic operations, most specifically addition, subtraction, and sign extension. I expect you to understand what addition and subtraction is. Sign extension may be a new term. We're also going to look at overflow conditions for addition, multiplication, division, etc.
that can be built from these basic operations. And then we will get into some logical operations and, or, and not. Here's the beauty of using 2's complement for integers. 2's complement addition is just binary addition. We have to assume all the integers have the same number of bits. So you may have to sign extend a number with zeros or ones if it's negative, but we'll get to that in a second. So here, let's take a look at the operation on the left. 104 minus 16. Well, that's simply 104 plus negative 16. So what we have is the 2's complement of 16, making it negative 16. And we simply go bit by bit. Bit 0, 0 plus 0, 0. Bit 1, 0 plus 0, 0. Bit 2, 0 plus 0, 0, etc., etc. And you can see, there you go. Now, in this example, the most significant bit is a 0, as it should be. 104 minus 16 is a positive number. Now, let's do negative 10 minus 9. I'm going to do that on a separate slide together with you. Let's go there right now.
So I've placed the addition problem over on the right hand side. Before we get started, what we have to do is we have to determine or establish what negative 9 is. So if I start from right to left, which is how I like to think about it, right? We've got 9 is an odd number, so we're going to have a 1, 0, 0, right? 1, 2, 4, 8, right? So if we're going to flip that number, those bits, we're going to have 0, 1, 1, 0, right? And we're going to add 1. So 1, 1, 1, 0. Okay? So here we are. Put the problem on the right hand side because we'll use the left to convert 9 to first its binary unsigned equivalency, and then we'll make it negative 9. So I know since 9 is an odd number, bit 0 is going to be 1, right? Whoops, bit 0 is going to be 1. Okay. 2, 4, 8. 8 plus 1 is 9. Pretty simple, right? So if we flip those bits, right? 0, 1, 1, 0. Add 1, we've got 0, 1, 1, 1. So we've got, come over here, we've got 0. I'm sorry, undo. We've got 1, 1, 1, 0. And then because it's a negative number and we need 8 bits, we just sign extend it. And it's a negative, so we sign extend all those. And then all we do is 0 and 1 is 1. 1 and 1 is 0. Carry the 1. 0, 1, carry the 1. 1, 0. Carry the 1, 1, right? Carry the 1, 1, carry the 1, 1, and that's it. Okay. So let's now determine what this is. So let's flip the bits. 0, 0, 0, 1, 0, 0, 1, 0, and add 1. So I'm going to cheat. I'm going to write the 1 right here, right? So we've got 1, 2, 4, 8, 16. So 1 and 2, 1, 2, 4, 8, 16, 16, 17, 18, 19, negative. Got that? Wish my handwriting were a little better, but I'm using one of these digital tablets and it's not as easy as writing on the board, but hopefully you get the idea and hopefully I'll get better at this.
So what if we have subtraction of a negative number? Well, that's not very hard. Subtracting a negative number is like adding the positive equivalent of that number. So here we have 104 minus negative 6. Oh no. Oh, sorry, 104 minus 16, so we just simply add 104 and negative 16. So what if we have negative 10 minus negative 9? Well, that's simply negative 10 plus 9. So you take the negative 9, or you just take 9. I mean, you could take the negative 9, you flip the bits, whatever. But you just simply convert, and if it's represented as negative 9, you flip the bits and you add 1, and then you've got positive 9. I'm not going to do this one for you. I'd like you to do it at your desk or wherever you're sitting as you're watching this lecture. And you have the decimal equivalent for the answer, so you should be able to double check your work. Next up, sign extension. It's a very important term. In order to add two numbers, we have to represent them with the same number of bits, especially if they're 2's complement numbers. So if we just pad zeros on the left, 0, 1, 0, 0, which is 4, is still 4. But 1, 1, 0, 0, which is negative 4, does not come out as negative 4. It comes out as 12. So instead, what you do when you sign extend a 2's complement signed value is you replicate the most significant bit, which is the sign bit. So there we have 4, 0, 1, 0, 0. And to sign extend that so that it's 8 bits, we just extend or replicate the most significant bit, the sign bit, all the way across till we get to 8 bits. You do the same with the sign bit of a negative 2's complement value. 1, 1, 0, 0 is negative 4. Negative 4 represented in 8 bits is 1, 1, 1, 1, 1, 1, 0, 0. This is really important because when we get into machine language, some instructions are going to have an offset. We've got 5-bit, we've got 9-bit, we've got 11-bit offset or operands that get sign extended to 16 because we're going to be using a 16-bit instruction set architecture when we get to that point in the class. And at the end of the day, every piece of information, every instruction, every piece of data that is fed to the processor, because it's a 16-bit processor, has to be 16 bits wide. So if we have a 5-bit 2's complement number, it has to get sign extended before it gets moved into the processor and acted upon. Next up, overflow. If the result of two operands, the sum, let's say, is too large to be represented in the number of bits being used, you get what's called overflow. And so if signs of both operands are the same and the sign of the sum is different, you've got an overflow issue. And another easy test for the hardware is if the carry into the most significant bit does not equal the carry out. So here's two examples. In this example, which is an academic example, we are using a 5-bit system. Let's say that's the capacity of the system we're using. So we've got 8, 0, 1, 0, 0, 0, plus 9, positive 9, 0, 1, 0, 0, 1. The result, because it's 2's complement, comes out to negative 15. Obviously, that doesn't work. We've got overflow. We've exceeded the capacity of a 5-bit system. Can't represent negative 15 in 5 bits 2's complement. Another example, negative 8 plus negative 9, which is the equivalent of negative 8 minus 9. If you add each of the bits, it comes out to a positive 15. That's not correct, can't be correct, so we have overflow. Logical operations on binary values are handled 1 bit at a time. This is called bitwise logical operations. So, for example, AND is a binary logical operation. Binary, bi as in bicycle, having 2 wheels, has 2 operands, A and B. So A and B both have to be 1 in order for the resultant to be 1. So we say A or AND is rather exclusive. There are 4 combinations of a bitwise AND. 0, 0 yields 0, 0, 1 yields 0, 1, 0 yields 0. It's only when A is 1 and B is 1 do we get a result of 1. Or is a little bit more inclusive. Or the result of a bitwise OR, which is another binary 2 operands operation, the result is 1 if A or B is 1. So it's much more inclusive. It's only 0 when A and B are 0. Not is a unary, like a unicycle, has 1 operand. Not flips a bit from a 1 to a 0 or from a 0 to a 1. It negates that bit. Here we have some examples of logical operations using 2 8-bit numbers. AND is useful for clearing bits. If we AND a value, when we get to programming, we're going to have 16-bit values stored in registers. If we AND that value with 0 and store the result back in the same register, we will be zeroing the result. So here's an example of an AND 1 1 0 0 0 1 0 1, and it with 0 0 0 1 1 1 1. And you could see if we start at bit 0, 1 and 1, 1, 0 and 1, 1, or 0, 1 and 1, 1. So the only time you get a 1 in the result is if A and B are 1. Or if you OR something with 0, you get no change. If you OR, you can OR it with 1. So in this example, I'm just checking. We have the same 2 values, but we're ORing them in this example. And you'll notice that we get many more 1s in bit locations for the output because it's 1 or 0. Not is a unary operation. Not just flips the bits. You can imagine, I hope you can imagine at this point in the lecture, how we would use not. Right? If we want to get the 2's complement of a value, we not it, and then we add 1. Next, we have the hexadecimal notation or hexadecimal numbering system. This is a base 16 numbering system. So if you recall, I said base 2 or binary is easier to learn and to manage because you only have 2 digits, 0 and 1, versus the numbering system that most of us grew up learning, the decimal system, where you have 9 digits, 0 through 9. Well, the hexadecimal system was created primarily for memory mapping. Every memory map, every memory address I've seen in the past 30 years has been a hexadecimal system or hexadecimal number. And it's easier to write a very large binary number in hex because you can combine 4 binary bits for 1 hex digit. You're probably thinking, how's that work? Well, base 2, 0 and 1. 2 to the 4th is 16. So yes, each hex digit can represent 4 binary digits. So on this chart, we're counting up until 15 because it's a base 16 system. It has 16 digits and they're 0 to F. Yeah, I know, that's a letter. You're probably thinking, wait a minute. Yeah. So let's count together. Binary 0000 equals a hex 0, decimal 0. 0001 in binary, hex 1, decimal 1. Not so different. And that is consistent up to 9. Binary 1001 is 9 in hex and 9 in decimal. Here's where things change. The decimal 10, which is binary 1010, is hex A. And then hex B is 11, C is 12, D is 13, E is 14, F is 15. What do you think 16 in hex is? It is 10. Let's take a look at that. One way of thinking of hex is that it's not a new numbering system, it's just a more convenient way of representing large binary numbers. Base 16 versus base 2. So here we have a binary number, a large binary number, and we want to convert it to hexadecimal. Here is the easiest way to do it. You parse this 4 at a time. So 1, 2, 3, 4 bits. Okay. That becomes a 7. 1, 2, 3, 4. Oops, that wasn't the best. 1, 2, 3, 4. D. 1, 2, 3, 4. Sorry, that was my cat. Sorry. I probably should re-record this, but I'll leave it there. Maybe it'll make you laugh. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then the last two, if you need to add a 0, you can. And you then just convert that. Okay. 7. This is D. You might want to use that chart to get started. F is very recognizable, 1, 1, 1, 1. A is 10, 1, 0, 1, 0. And the rest are pretty straightforward. So that's how you convert
from a binary to a hexadecimal number. It's rather straightforward, and here's why this is important. When we get to machine language, every memory map I've ever seen, dating back to before most of you were born, was mapped in hexadecimal. Some of you might remember the blue screen of death, and you would see this strange X0A473D01F on the screen. That was the address of the last successfully executed machine language instruction before the computer became unstable for whatever reason. So when we get to machine language, you're going to have situations where you're going to have to add a 2's complement binary number. Here's a great example. 2's complement, a 9-bit 2's complement, sign extended number, sign extended to 16, and then added to a hexadecimal number. So if it's a 16-bit 2's complement number, it will become a 4-bit hexadecimal number. And you'll have to add it to a memory address that is, well, in hexadecimal. So this is really important. We need to understand this. If you have any questions about this, or you want me to go over any of this live during my office hours or during another session, just get a hold of me and let me know. One way of representing fractions is fixed point. Use a binary point to separate positive from negative powers of 2, just like a decimal point. 2's complement addition still works if the binary points are aligned. So this is one way this could be done. It's not the way the vast majority of modern computers handle decimal numbers. We're going to take a look at that next. For very large and very small decimal numbers, we use what's called floating point precision. And the standard, or the first standard for representing base 10 decimal numbers in binary, was the IEEE, and IEEE stands for Institute for Electrical and Electronic Engineering. IEEE 754 standard for floating point numbers, and it's a 32-bit standard. And so we have 32 bits to represent numbers in a binary scientific notation, if you will. And we're going to go through each of the components and actually dissect a floating point number. So bit number 1, I should say bit number 31, the first bit to the left, is the sign bit. 0, positive, negative 1. Or 0, positive, 1, negative. Then you have an 8-bit biased exponent, and I'll get to the description, explanation of bias. Then you have a 23-bit fractional component. And what I'm going to do is I'm going to walk you through the process in a slide or two, and we'll actually convert a number that's in base 10 decimal to IEEE 754 32-bit floating point.
Now I'm going to walk you through the process of translating a decimal base 10 number, in this case 85.125, to a single precision IEEE 754 32-bit floating point value. Double precision is 64 bits, but we'll go with the original standard, which was IEEE 754. Once we had a 32-bit processor in PCs and fairly robust processing speed, we were able to do very significant, high tolerance, high precision, large scale engineering, scientific, defense type programming with computers, PCs. So let's walk you through this real quick. Let's dissect the 32 bits. The most significant bit is our sign. Then we have an 8-bit exponent. And then we have a 23-bit mantissa. So in this case, we're going to take a number, 85.125. I can tell you by looking at it, this number is going to divide into a power of 2 nicely. So first thing we do, first part in the process, separate the whole and the decimal part of the number. And we'll start with the whole number and convert 85 into binary. Okay? So you simply start dividing by 2. From 85 divided by 2 is 42, remainder 1. Then 42 divided by 2, 21, remainder 0. 21 divided by 2, 10, remainder 1. 10 divided by 2, 5, remainder 0. You can probably see where this is going. 5 divided by 2, 2, remainder 1. 2 divided by 2, 1, remainder 0. 1 divided by 2, 0, remainder 1. And that's when we stop. And then we build this number from the bottom, from the bottom up. So this one is this one, and this one is this one. So, and then we just park that number on the side, and we'll convert the decimal portion into binary. The decimal portion is done by a series of multiplications by 2. So 0.125 divided by, or multiplied by 2, 0.25. So we're going to take the whole number component, put it over here. 0.25. 0.25 times 2, 0.5. There's the 0. 0.5 times 2, 1.0. Put the 1 over here. And then we have 0, and it would be 0, 1. So then we compile this top to bottom. So it's 0, 0, 1. And we're going to put that next to this, 0, 0, 1. But I'm sure that's done. Yes, right here. We have an imaginary decimal point because there is no decimal point in binary. So we're then going to normalize this. We're going to convert the binary number into base 2 scientific notation, just like 1,770 becomes 1.77 times what? 10 to the third. We're going to move that imaginary decimal point until the number is normalized. 1, 2, 3, 4, 5, 6. So it becomes this times 2 to the 6th. But because, and if you move it to the left, it's positive. If you move to the right, it's negative. So we have to then add the bias to the exponent. Now, the developers of this system could have used 2's complement for the exponent. They did not. For various reasons, they decided to use a bias. And the bias gets added to the exponent. The bias for an 8-bit exponent is 127. With 8 bits, we can represent 128 numbers, 0 to 127. So we add 127 to 6. And this becomes our exponent. And we need to convert that to 8 bits and place it there. Number was positive. There's our sign bit. And there is our 8-bit exponent biased. And then we take that mantissa and we just put it here. And because the mantissa divided evenly as a power of 2, 0.125, we don't have any repeating decimal points here. So we just place that mantissa and then we put zeros at the end. There are going to be instances where you have a mantissa that is a repeating number. So for example, 0.125 is a power of -2. Just like 1 divided by 3 is an ever-repeating decimal in base 10, a number like 1 divided by 5 is not going to be, 1/5 is not going to be able to be represented exactly in no matter how many bits you have of precision. So in the timeline, I'll put some additional problems. Let me say, this is a cryptic process. You will be assessed on this process, and I absolutely positively guarantee you, in the moment, on exam 1, when you say, well, I'll just use one of those online calculators, trust me, you will not have access to the online calculator. And if you try to access that, it will be problematic. So you really need to practice. And you're not going to understand this process and be able to do it without doing 5, 6, 7, 10 of them. So don't cheat yourself. Okay? And I'll place some other ones in the timeline. And there's actually a video I placed in the timeline of a number that doesn't exactly fit, can't be exactly or precisely represented in base 2, and how that repeating decimal point or repeating pattern of numbers is handled. Now we have a demonstration of going the other way from an IEEE 754 32-bit floating point, single precision floating point number to its decimal equivalent. So let's take that 32-bit number. This looks intimidating at first, but it's not. Take it one component at a time. The sign is -1. I'm sorry, the sign is 1, so it's a negative number. The exponent field, 0.1111110, is 126 in decimal. So we're going to, instead of adding 127, we're going to subtract 127, and we come up with an exponent of -1. So, and the fraction is 0.5. So we have -1.5 times 2 to the -1st. 2 to the -1st is 0.5, so 0.5 times 1.5 is -0.75. Pretty straightforward. Easy for me to say, right? ASCII. ASCII is a numbering system that was developed for input and output devices. It was developed primarily for keyboard. And every keystroke on an ASCII keyboard maps to a 7-bit code. And what we have here is the numeric equivalent of those codes in hex. So 00 is actually 8 zeros. 01 is 7 zeros followed by a 1. And so that when we get to, let's see, hex 30, which is 00110000, is actually the equivalent of 0. Yeah, isn't that great? That 0 in ASCII is not 0 in decimal, but we're going to hold ASCII over on the side, kind of like park it over on the side, because when we get to I/O, ASCII is going to be a real pain in the neck. And I'm going to have to review ASCII to decimal back to ASCII, and we'll actually write subroutines to handle the transition from an ASCII input to a numeric value that we're going to use for calculations. And then we have to convert it back to ASCII to send it to the ASCII monitor. So this is the ASCII character map. It will be featured front and center when we get to I/O later in the LC3 portion of this class. Just some interesting properties of ASCII, which I've touched upon in my previous, in our previous slide. The relationship between a decimal digit 0 and its ASCII code. It's hex 30, which is decimal 48. What's the difference between an uppercase letter A and its lowercase equivalent B? Given two ASCII characters, how do we tell which comes first in alphabetical order? So, and then we get into modern day devices that needed more than 128 characters, and then the Unicode numbering system was developed. But for the sake of this course, we're going to focus primarily on ASCII. Today, we're representing many types, data types, in binary format. So we have text strings, we have images, JPEG, PNG, various BMP, which was one of the first, bitmap, one of the first numbering systems for representing images in electronic format. And then we have varying sound and video formats. So at the end of the day, you should understand that these are all just numbering systems. Just like IEEE 754 developed a numbering system for 32-bit single precision floating point decimal numbers. I can't remember who developed MP3, but MP3 was a numbering system that had minimal, and I'm not an audiophile, had minimal degradation of the audio quality. And a friend of mine who's an audiophile and has a $10,000 stereo system would argue this point. But the fact of the matter is, to the untrained ear, MPEG and, MP3 and the original WAV, wave format, don't sound any different. And I've actually taken wave early CDs I had back in the 1980s. And I think the process is called rip. You rip them, you transfer them to MP3, and the file size is dramatically smaller, which makes it a lot easier to store them on devices other than DVD drives. So at the end of the day, all of these proprietary formats are just numbering systems that have an encoder and a decoder. That's it. So they're we're beyond the point where someone said, well, how do we store that on a computer? We're way beyond that. Somebody comes up with a format like MP3, which pretty much made WAV obsolete. And who knows if someone will come up with a tighter encoding compression for music. But now that we have high-speed internet and people are moving those files over the internet, it's really not that big of a concern. So you can even stream, HD movies now. So just know that all of these files that you have on your drive of your phone, your computer, your iPod, whatever, they're just zeros and ones in some proprietary format that get decoded from the source or encoded from the source and then decoded when played in whatever type of player. In this class, we're going to use a simulator called the LC3. LC3 stands for Little Computer, and it's the third iteration. There was an LC2 and an LC1. And it is a wonderful tool, and it allows us to see things, snapshots of the state of the machine that would be otherwise impossible to capture, analyze, envision. It's not a full-blown computer. It's not a 32-bit processor. But what it does, it allows us to use the basic 8086 Intel instruction set architecture, of which almost every personal computer's instruction set architecture is a descendant of, a development, an advancement of. So, and it allows us to do some machine language programming. We're going to have 16-bit 2's complement signed integers. We are going to have basic machine language operations, add, and not. And we will be able to input values from an ASCII input device and export or output devices, data to an ASCII output device, i.e. an ASCII monitor. So that's why we're spending this time up front to make sure you understand the numbering systems. They are a critical component to understand basic computer organization. That's the end of this lecture. Thanks for watching. Have a great day.